Today's lesson is on simplifying radicals. But before we get started, you know I like to start with a joke sometimes. Well, a riddle, I'll say. What's the difference between a sock and a camera? One takes 5 toes while the other takes photos. Okay, I'm sorry. Ooh, that was funny. Okay, properties of radicals. First of all, we have the product property where it shows that you can multiply them together or separately, and the same is true with division. For example, for the second property, if you had the square root of 16 over 4, we know that that's the square root of 16 over the square root of 4, which is 4 over 2, which is 2. Or you could just divide first and do the square root of 4 is 2. And I just want you to know that it's the same whether you separate or whether you do it all together. Okay, let's use some of these properties. And by the way, you've always known about these properties and we've always used them. So now I'd like for you to see how they work. When we simplify radicals, we look for perfect squares like 4, 9, 16, 25, 36. We're looking at the perfect squares. And so we want to know which is the largest that goes in evenly. And 9 works. So 9 times 6, that would be 3 radical 6. And that would be how you simplify that. But when we simplify cube roots, we're looking for perfect cubes that go into 54. Our perfect cubes, besides 1 cube, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. So we're looking for a perfect cube that goes into 54, and we know 27 works, and 27 times 2, and the cube root of 27 is 3. And don't forget to write the index right here, because if you don't write the 3, then we assume it's a square root. Okay, again, this is a cube root, so we're looking for perfect cubes. So what we're looking for here, first of all, we know that the negative can just come out front. So we're really just taking the cube root of 750, and 125 goes in 6 times. So we got our negative sign, we got 125 times 6. So my answer is negative 5 times the cube root of 6. And that's how we simplify that. And with a little practice, you'll be an expert. Okay, let's go ahead and look at how to simplify when we're dealing with variables. Now that we have variables, we're going to have to remember the even, odd rule if it comes into play. Okay, let's look at part A. What we want to do, and listen closely because this could be a little confusing. We're looking for the highest number divisible by 3, but it has to be less than 11. Again, we're looking for the highest number divisible by 3. In other words, we're looking for a perfect cube. So here we have the cube root of x to the 9th power, because 9 is divisible by 3, times the cube root, and we ask ourselves what's left. If you multiply x to the 9th times x squared, you get x to the 11th power. So now, when we do this, the radical is completely gone. Okay? And when we simplify, we want to leave it in radical form. Remember that. You want radical form. Alrighty? So I'm going to leave this as the cube root of x squared. Alrighty? And because this is odd and this is odd, I don't have to worry about the even, odd rule. Alrighty, let's look over here. This is a square root because there's no number here. So I'm asking myself 4, 9, 16, 25, 36. I'm asking myself what's the highest perfect square? 4 is the highest one. 4 times 21. This is a square root. So I'm looking for the highest number that's divisible by 2. So I'm going to break this apart to x to the 8th because 2 goes into 8 evenly. You want to take out as many 2's as you can, as many perfect squares. That leaves me at x to the first power, so that when these are multiplied together, you get x to the 9th. Now, this is a perfect square, and this is a perfect square. This is about separating the perfect squares. So now, I have a 2 here. This is perfect, so that's 8 over 2, which gives me x to the 4th power. See how I made that, designed it so that it's perfect. And now, these two parts are not perfect, so I'm going to leave them inside the radical. I check for even, odd. That's even, that's odd, that's even. So no worries on the even, odd. Alrighty, hopefully you're starting to catch on. Let's do this last part. This is going to be a little trickier. We're back to cube roots. So I'm asking myself about perfect cubes that go evenly into 48. So 8 is my perfect cube. That leaves me with 8 times 6 is 48. Okay, now I'm going to separate this x to the 17th power into the cube root of x to the 15 because I'm looking for a number divisible by 3, and that leaves me with 2 x's inside. Now I'm looking at a 4, so I'm going to split that into y to the 3rd with 1 y left over. And, oh, this one's already good because 3 already goes into 6 evenly. So now I've done this in such a way where I've got a lot of perfect cubes, So now I'm going to take the cube root of those perfect parts and I get, oh, nope, I don't get that. The cube root of 8 is 2. Now I'm over here looking for the cube root here. That would be x to the 5th power. 15 divided by 3. Remember, the index is the denominator. 3 over 3 gives me y to the 1st power. And now 6 divided by 3, that gives me z squared. Now I have the rest of it is left inside the radical because it was not perfect. Alrighty. And all the exponents under the radical have to be less than 3. If not, that means I need to simplify some more. Alrighty, let's look at rationalizing the denominator. If you recall, you've learned before that radicals are not allowed in the denominator. And if you look at A, B, and C, they're radicals in the denominators. We got to fix that. As well, you cannot have fractions under the radical either. So we need to fix all of this up. So what we're going to do is we're going to make the denominator a perfect square by multiplying by radical 5. Because 5 times 5 is 5 squared. So we know that's going to work. And whatever you do on the bottom, you do on the top. So I have 3 radical 5 over square root of 25, which is perfect because we designed it that way. Final answer. Now, we can use the division property for radicals and simply mash these together. And the reason I'm doing that is because 5 goes in evenly. So now, that's a quick way of doing that. I could have also done the radical 5 over radical 5, and then I would have just got radical 100 on top over 25. So I would have got 10, 10 over 5 would have still been 2. So it'd come out the same. Now I need you to really focus on this because this is a cube root, not a square root. So it does not work the same, I repeat. Now what we want to do is make the denominator a perfect cube because this is not a square root. So remember your perfect cubes, 8, 27, 64, 125, 216, and so on. So what we want to do is we want to fix this so that like here we got 25 and that's a perfect square. So if I multiply by 3, I'll get 9 on the bottom and we don't know the cube root of 9. So I'm going to multiply by 9 because 3 times 9 is 27. And whatever you do on the bottom, you got to do on the top. So I have 2 times the cube root of 9 over the cube root of 27. And we know the cube root of 27 is 3. Therefore, we no longer have a radical in the denominator. Alrighty, here, since I can't do anything with this fraction, I'm going to separate it into separate radicals. And now I want to figure out what I can multiply 4 by to get one of these perfect numbers. Okay, if I multiply 4 by 2, I'll get 8. And 8 is a perfect cube. That's why I'm selecting 2. And notice this is 2 squared. That's 2 to the first, which gives me 2 to the third. So that's what's really going on. So in the numerator, 1 times 2 is 3. And in the denominator, I have the cube root of 8, which is 2. Final answer. All righty, moving right along. What do we do if the denominator is a binomial, so to speak, with the plus sign and they're not like terms? Then what we do is multiply by what we call the conjugate. That means just change the sign in the middle. Don't change the sign in front of the 3, just the one in the middle. And whatever you do on the bottom, you do on the top. Again, that's called the conjugate. Alrighty. And before we talked about how to multiply those together. So in the numerator, I have 3 minus radical 5 because all I did is multiply it by 1. But in the denominator, I have to first outer and inner are going to cancel. That's what conjugates do. And look at what happens when we do last. We did first, we did outer, we did inner. And last, that's positive times negative is negative. And radical 5 times radical 5 is radical 25. Ha ha. Perfect square. So this is just 5. Okay, these cancel. So now all I have is 3 minus radical 5 on top and 9 minus 5 on the bottom. So that's 3 minus square root of 5 over 4. Final answer. And funny thing, when you get to pre-calc, you're going to do this with trig functions, not just a little 3 and a radical 5. So remember, the principles stay the same, conjugates, and how to get rid of things that are not like terms. You're going to do it the same way. Now, I want to make sure you understand with radicals that you have to have like terms, just like variables. You have to have like terms to add or subtract. So these are both radical 2's. So 7 radical 2's minus 5 radical 2's just give me 2 radical 2's. All you do is combine those like terms by simplifying the coefficients. These are not like terms, so there's nothing I can do. It's already simplified. Alrighty, let's look at another example. Sometimes they might not appear to be like, but sometimes if you simplify first, you'll find out that they are. So the square root of 75 can be broken apart to 25 times 3. And that's 2 times 5. So that's negative 8 radical 3 plus 10 radical 3, which gives me a 2 radical 3. Alrighty, let's keep it going. Here, we have a radical in the denominator, and this is going to take a little work. So pay close attention. What I want to do is make this number divisible by 4. That would make it perfect. But you can't go backwards. You can only go higher. So the next number divisible by 4 after 9 is 12. Okay? I need this 9 to turn into a 12 so that it'll be divisible by 4. So that means I'm going to add 3 to it. 9 plus 3 is 12. And whatever you do on the bottom, you have to do on the top. I know I'm showing you a lot of stuff today, but I know you can handle it, and we'll practice. So on the bottom, I have the 4th root of 9 plus 3, that's x to the 12th power. And the reason we did that is because now 12 divided by 4 is 3, and it's perfect, so we're able to get rid of the radical. Uh-oh, I didn't write that correctly. Hold on. That's 6 times the 4th root of x cubed. Now, you might wonder, why can't we cancel these two? One's under the radical and one is not, so you cannot cancel those. Okay, now, let's look at this. I got x's in the numerator, y's down here. What I'm going to do first of all is split this because they're different, so I'm going to treat them separately. The numerator, that's pretty easy. 10 divided by 5, that's x squared. But here, I've got to worry about the 2 is not a perfect 5th root, nor is that 7. That's not divisible by 5 either. So what I'm going to do is try to figure out 2 times 2 to, 2 to, I want to get to 2 to the 5th power. So I need to multiply. Let me rewrite this first. Sometimes you want to treat numbers just like exponents. So I want to go 2 to the 4th power. And I need this y. That's the 7th power. I want to make that 7 turn into a 10. So that means I need 3 more. Let me make sure you understand why I chose those numbers to multiply top and bottom by. Now, when you look, and I'm going to swing around here. When we look here, in the numerator, I have x squared times the 5th root of 2 to the 4th power. 2 times 2 is 4, 8, 16. That gives me 16 y to the 3rd. And downstairs, notice this is really the 1st power. So I have 2 to the 5th. 1 plus 4 gives me 5. And 7 plus 3 is 10. So now we can see 5 goes into here evenly and into here evenly. So that's going to cancel, and everything's going to work out real good. So I have x squared, 5th root of 16y to the 3rd, and that gives me 2y squared. Notice the 5 goes into 5 one time, and 10 divided by 5 is 2. Alrighty, last example. I know we've been working hard today. We're going to write in simplest radical form. Now, we have a lot going on. We've got fractions, we've got negatives, everything. What I'm going to do is I'm going to treat this like different problems. I'm going to work with the numbers. I'm going to work with the x's. I'm going to work with the y's and the z's. So 6 over 9 simply reduces to 2/3. Here, I'm going to use my property, knowing I can subtract exponents. See, that has an exponent of 1. Here, y negative 1 minus 5, z squared minus 3. See, all I'm doing is I'm subtracting exponents. You always start with the numerator and subtract the denominator. Now here, I need common denominators, so I'm just going to call that 3 over 3. So I get x to the 1/3, y to the negative 6, and z to the negative 1. Now, now I want to make sure I write this in simplest radical form. When you write in simplest radical form, that means no rational exponents, as well no negative exponents. So let's take care of that. First of all, let's see what's in the numerator. I have a 2 and I have x cubed. How can I write that as a radical? That would be the cube root of x to the 1st power. Now, the negative means reciprocal. And now I can make that positive. And here, that's going to become z to the 1st power. I don't have to write the 1. Final answer. And that's simplified.